In this video, we're going to talk about traversing a matrix in spiral order. So we're given a matrix that is m rows by n columns. So this is a 3 by 3 matrix, which is just a square. And then this is 3 rows, which is m, and then 4 columns, which is n. And we're asked to do the spiral traversal. So that means we start in the top corner up here, and then we're going to go across the matrix. We're going to go down. We're going to come this way and up. And we're going to make a spiral, almost like a shell. So we would do the top row, and then we would go down, and then we would go this way. And then when we go up, we don't go all the way to where we started. There's a boundary here. And this is an observation that we make. This might factor into our solution. Well, it's going to factor into our solution. And then we go here and then come to the center. That's a spiral traversal. And then the same thing here, we start in the top corner, we do the whole first row, and then we go down, we go to this right boundary, and then we come this way, we come that way, and then through the center. And then we visited all of the items. And so how are we going to do this? First off, if we think about how much time this is going to take, at every element, we're just doing a read operation, or we're going to add this to an array. That's going to be constant time. So we know that the least work we're going to do, if we're going to visit all of these elements, is m times n. That's just something to take note of. How would we go about this? We have two options here. We just saw the traversal. And if you think about linked lists, linear data structures, when we traverse linear data structures, we keep a pointer. We track that pointer, and it takes us to where we want in the data structure. Here, we could think about that as well. We could think about doing a single pointer approach. Okay, so if we do this pointer approach, we would start the pointer where the iteration wants to start. And then we would continue the pointer all the way until we hit a right boundary. So let's just imagine there's going to be a right boundary. And then once we hit that right boundary, then the pointer goes downwards. Then the pointers change every iteration is in the downwards direction in coordinate. So it'll go down, and then it'll hit a bottom boundary, right? It'll hit a bottom boundary, and then our pointer will be here. And then our pointer will go this way, and then it'll come up here. And then it'll hit the original top boundary where we started. So this pointer approach could work, and it might be a little tricky to implement, but we just noticed something. We're drawing boundaries, and the fact that we're drawing these boundaries makes us think, is there a way we can extract state that keeps track of these boundaries? And if we can keep track of these boundaries, we know exactly where to begin our iteration. And we see that it compartmentalizes into 4 iterations: a top iteration, a right iteration, a bottom iteration, and a left iteration. If we can make sure these fences are at the right positions at the right time, then our iteration is going to do what we expect it to do. So let's walk through this with boundaries through our second run. So I want you to imagine this. We're imagining there are fences. And if you want to really get a deep look into this, we're going to go over the code, but I'll put the code in the description just so you can see the variable naming. That'll help you kind of sift through this. But we think of this as having fences around where we want our iteration to go. And we're going to start our iteration at where? Where are we going to start it? We're going to start it at the top. Our row is going to be dictated by where the top fence is, and then our column is dictated by where the left fence is. We'll keep track of our fences over here. And so we start our iteration here, and we'll put our output here. So what we're going to do is we're going to have a for loop that's going to walk from the left. The column is going to be the changing factor in the top row iteration, right? Because we're changing columns. So we're going to do a for loop from here to there. We're going to go from 1, visit 2, visit 3, right? Because that's going to do the top row iteration. And then we're going to see how we need to change our constraints. So we say 1, 2, 3, and this is what the top for loop does. And now I'm sitting here. But think about this. We don't want the right fence to be reading from the 3. We don't want to print the 3 again. We already printed it. So as soon as we finish the top row iteration, we're going to move the top fence down, because this row is finished. We don't want to reread that 3. So let's move that fence downwards. Okay, so do you see how we moved the top fence down by 1? And now, where do we start the next iteration? This is going to be the right boundary iteration. So we're going to have 4 for loops, 4 iterations. So the right boundary iteration, its row, where should its row start? Its row should start where the top boundary is. But where does it go? It goes from the top boundary to the bottom boundary. So it's going to read the 6 and the 9. Okay, so that for loop's done, but what needs to change here? We need to change the right boundary, and I labeled it wrong here. The right boundary, I should have labeled it up there, but this right boundary, we don't want to reread the 9. The corners are giving us trouble. So we don't want to reread the 9 because we already read it there. So we're going to move the right boundary, which is what excludes the column we just read. We're going to move that inwards. And now that we've done that, we're right here. So our iteration for the bottom, where's our column going to start? It's going to start at the right, and then the column's going to pull back. When does it stop? It stops at the left boundary. And then that's going to read the 8 and the 7. And then again, the same problem happens. We don't want to read this 7. So we're going to push the bottom boundary upwards. And finally, we're going to do the top iteration. We're back where we started. We did the top. This is the top. That's the top line iteration, the right iteration, the bottom iteration. And then I added the 4 for the left boundary iteration. If this was a taller matrix, the left would have read more all the way up to the top boundary. Okay? And we're trying to craft a routine that will always work. And now we're going to pull in by one more layer. We're going to pull one layer inward, and we're going to do the exact same thing, because this is how we're simulating spiral order. The spiral order has shells to it. We're trying to simulate each shell, and we don't want to reread entries. Those are the provisions we're making. So at the end of reading the left, we would have incremented the left boundary so that we move that inward. So we incremented the left boundary, and now we're in the very middle. We're going to iterate from the left to the right, and this is the top row iteration. So we're going to print the 5, and then we reach the end of that boundary. So what happens? We're going to move the top boundary down by 1. And then at this point, there's no more elements to read. We're going to, if we do the right iteration, or the right side iteration, we go from top to bottom, but we can't do that because the top has passed the bottom. Then if we try to do the bottom iteration, we might actually reread this entry, but why? Why would we do that? The bottom iteration is just going to say start at bottom. Well, bottom's sitting right there. Okay, start my column at the right column, because bottom iteration starts over here. It's going to start at the right column, and it's just going to reread this guy. So that's another provision. We're going to need to think about that in the for loop. So it's good that we drew out this example. We might want to draw more examples, but knowing this routine we're thinking about, it will probably work in most cases, but there might be edge cases that exploit certain aspects. Let's look at the actual implementation and continue to think about these things as we go through it. So our function passes us a 2D matrix, and all we're going to do is be reading from this matrix. So we can create a new list for the output sequence. We could just print it, we could output it, but in this case, we're going to create a list for the spiral ordering. So we're going to create that variable. So we created that variable. And then now we're going to create tracking variables for the top fence, the bottom fence, the left and the right, like we were talking about before. So we're going to create these 4 variables, and we're going to keep track of each of these boundaries. And then these boundaries are the states that are going to tell us about how to execute the iterations. Okay, so we created those variables and we'll track them. And we said matrix.length, because remember, the top level matrix is it's an array of arrays. The top level matrix has the rows, so that's going to give us the bottom, the last row, the bottom fence, and remember top 0. So then the left is just 0, and then the right, we assume this is going to be a well-formed matrix. There won't be varying size between the rows, so we're going to just take the first column's length, and that's going to be the total columns. We're going to assume that the matrix has rows, it has columns. We won't get any null pointer exceptions by indexing into something that doesn't exist or by accessing something that doesn't exist. So we need to think about, when does the iteration stop? We're going to want to iterate, and we want to continue the iteration while it's reasonable. And it's reasonable as long as the bounds are meeting. If the bounds pass each other, then it's unreasonable to continue and even execute logic in the while loop. But that doesn't mean we're safe. That doesn't mean we're safe in the while loop. It just means it's how long we want the iteration to go. So we'll see when we're not safe, and we'll add an extra if statement for that. And that'll often be the case when you're crafting these iterations and figuring out when they need to stop. It's tricky at first. So let's write that. And so now we're going to just do the first for loop, and then all the other for loops will fall in line with it. And the full code is going to be in the description, and it's exactly what we're doing here. So the first for loop, what do we want to do? We want to go from the left boundary to the right boundary. But what row are we walking along? We're walking along the top boundary's row. The top boundary denotes the row we're walking in. The left boundary denotes where the column we start at. The right boundary denotes where we end the top fence iteration. So let's write that down. So what needs to happen here? We're parameterizing the column because that's the changing factor. So that's going to be the parameter in the for loop, and that's changing right here. So the column is changing, but what's not changing? The row we're on. The row is denoted by the top fence. So the top fence is denoting that. And then we're going from the left to the right, and we're keeping this inclusive. And that's because we're tight to the indices. We're not doing something where we say matrix.length. We don't need to throw in a -1. Everything's in terms of indexes. And it's kind of cleaner to think about it this way, but you could do it either way. It's just how you want to think about it. And then this is critical that we move the top boundary after we finish the top row, so that right boundary iteration does not reread the top right corner of the matrix. And if we make sure of that, we make the same provision for the right boundary, the bottom boundary, and the top boundary iteration, and that's going to produce the result we desire. And then we need to throw some if statements in there, but that's in the description. It's just a small edge case you need to take into account. If the center is not just a single item, if it's a strip going horizontally or vertically, you need to add additional provisioning for conditions, these conditions down here. So let's think about time and space complexities here. If we exclude the output, how much space are we going to use? We're going to use constant space. We're just iterating over this structure. It's like iterating over an array. We're not creating anything new. We are creating a new structure, but often with space complexities, we don't take into account the output unless explicitly told. Because intrinsic to this algorithm, if someone said, I don't want you to output this sequence, if someone said, don't output the sequence, we use constant space. But just because someone told us to output the sequence, now we're keeping track of additional state, but it's not intrinsic to what we're doing. It's not like we're creating a stack in memory to make the core algorithm work. So that's just a small distinction, something you'll often see. But in our iterations, we're just going to iterate, and every single element, how many elements are there? M times n. For every element, all we're going to do is do a constant time add operation. And that's constant time work at each of these elements. In the case of adding a primitive value, you're just going to be adding this value into the array. And if the array needs to double, it might do a linear time double, but at the same time amortize this constant time to add to an array. And this is an array list abstraction, but let's just imagine it's a special array that doubles in size. So m times n, constant time, that's going to be the time complexity. Again, space is going to be constant. If we count the output, it's going to be m times n, because we're keeping all the entries. So this is the problem of printing a matrix in spiral order.